Now that we know where a matrix-matrix multiply comes from, let's look at how to compute it. And for this, we're going to go right back to the definition of linear transformations and how matrices are related to those linear transformations. Well, we like to slice and dice. So what if we go and we expose the different columns of matrices C and B? So here we expose the columns of C, we expose the columns of B, and notice that the number of columns in B must be the same as the number of columns in C, otherwise A times B is not well defined. What do we know about the jth column of C? Well, we know it must be equal to C times the jth unit basis vector. And by definition, that's just feeding E sub j into the linear transformation L sub C. And that, by definition, is the same as first applying linear transformation B to E sub j and then taking the result and feeding that into L sub A. And that's the same as taking B times Ej, because that B represents the linear transformation L sub B, and then taking the result of that and feeding it into a multiplication by A. Finally, we know that if you multiply B times the jth unit basis vector, we get the jth column of B. So what we conclude is that the jth column of C is simply computed by doing a matrix vector multiplication of A times the jth column of B. And we know how to perform a matrix vector multiplication. So let's summarize that up here and let's move on. If we now go and we look at C sub j, then we can expose the individual components of C sub j. Now, what we're going to do is we're going to expose rows of A. And we've before given those the name A. We can index them from 0 to m minus 1, because that's how many rows there are. We need to put transposes on that, because they are row vectors. And we often went and put this little squiggle on top, just to be able to easily tell that these are rows. And we know that that must multiply times the jth column of B. But when we did partitioned matrix vector multiplication, we saw that this is a very special case, and in particular you simply end up doing A0 transpose times B sub j, A1 tilde transpose times B sub j, all the way through A sub m minus 1 tilde transpose times B sub j. Let's take that and let's summarize that. And if we now look at a typical entry gamma sub ij, the ij element of matrix C, what we now find out is that that's just the dot product of the ith row of A with the jth column of B. But we can expose the individual entries of the ith row of A. That has to multiply the entries of the jth column of B, and those will be denoted by beta, 0j, 1j, all the way through k minus 1j. And we can summarize that like that. But then we know that that's just this times that plus this times that plus etc. and finally this times that. And that's written right here. And finally, we can use the shorthand using the summation sign to write it as the summation from p equals 0 to k minus 1 of alpha ip times beta pj. And that's actually the definition that you were taught in high school. So we have just justified that definition for matrix-matrix multiplication by going back to the linear transformations that the matrices represent. Whenever you do a matrix-matrix multiply, you may want to draw yourself this picture. What we just saw is that we can go and look at the jth column of C, and that's just A times the jth column of B. So C sub j is equal to A times B sub j. Okay. And then we can look at that in more detail. If we look at the ij entry of C, So that would be gamma sub ij. That is equal to the row of A. We denoted that by A sub I tilde transpose, inner product with the jth column of B. So that tells us that gamma sub ij is equal to A sub I tilde transpose B sub j, and that dot product or inner product is defined as the summation from p equals 0 to k minus 1 of alpha sub I p times beta sub p j. It's important to keep this picture in mind every time you try to do a matrix-matrix multiplication. We'll see this over and over and over again as the course progresses.